Welcome to my YouTube channel. In this video, we are going to look how to calculate wind load based upon Russian standard.
The right hand side you can see the wind load calculation code as per SNIP standard. In the left hand side you can see the Excel sheet which is developed to demonstrate the wind load calculation. The first input required for the wind load calculation is site wind region. This is as per technical specification. Here I am considering the site wind region as 2. There are some 8 number of regions are there. You can select as per the technical specification. Next one is nominal wind pressure. For this we need to refer page number 16, that is table 5. So in this table you can see the values of nominal wind pressure. For region 2 it is 0.9, sorry 0.3. The unit for this nominal wind pressure is kilonewton per square meter. Next one is the total height of structure. For this I am assuming as a 10 meter. Locality category. For this locality category we need to refer page number 16. So here you can see the table 6 A, B, C. So these are the locality category. For the definition of the locality category you can see here in the right hand side PDF. A is the open coast of seas, lakes and storage ponds as well as deserts, steppes, forests, steppes and tundra. B, urban category, woodland and other lands covered with obstructions higher than 10 meter. C is urban territory holding building exceeding 25 meter high. So based upon your requirement, the location of the structure, you can select these categories. Next one is based upon this locality category, the coefficient of locality category you can find from the table 6 for structure height 10 meter which we had assumed, and locality category A, the value here is 1. So this is extracted directly from the table of code reference which is in the table farmer here. So this factor is pulled out from here, this table. So now this aerodynamic coefficient we need to find out. This is as per annexure 4 of SNIP 2.1.0785. For that page number 39 to be referred. So this is the page. So I am considering my rectangular shape of building. So it is the exposure, wind exposure is surface is rigid rectangular. So I am considering as 2. Next one is average component of the wind load for 10 meter span. So for that there is a formula to calculate this. So to find this average component of the wind load at Z, we are having a formula. So to find the formula, we need to go to page number 15. So here you can see Wm equal to WOKC. So applying this formula, I am getting 0.6 kilonewton per square meter. So next one is, as this is a pulsating, that is dynamic wind load calculation, I am going to calculate the natural frequency of structural members. So I am selecting this structural member for to support this structure is a main leg. Section chosen is U profile. This is phi U profile. I am selecting this. This kind of profile is like U profile with tapered flanges. So this is as per GHOST 8240, this material property we need to refer. There are also other sections are listed here. So for this U profile phi U, we can find in this table itself. So for phi, so this is the U profile with the tapered flange table as per GHOST 824089. So you can find the properties, various properties from here. So while selecting this itself, it will give you the property in this sheet. So for our calculation purpose, I am selecting this U profile tapered 5 pi. So weight of this is 4.84 kg per meter, and the height of the structural member I am assuming is 2 meter, is a leg member for the structure. And the modulus of elasticity, obviously we know that for steel it is 2 into 10 to the power of minus megapascal. And moment of inertia, usually it will pick from the table which is hide here. And the mass, weight of the structural element is nothing but it is weight into length of the structural member. And considering the cantilever stiffness of member, because this is supporting bracing, assuming that, so this shall be considered as a cantilever, then the stiffness of a structure member is K equal to 3EI divided by L cube. So applying this formula, this is a general basic formula for stiffness. Applying this, I am getting the value of 17,100 Newton per meter. So natural frequency, this is also basic formula to find the natural frequency. F1 equal to half of pi into square root of K divided by M. K is a stiffness and M is a mass. So applying these values in this formula, I am getting natural frequency of structure as a 6.69 Hertz. Following that, I am calculating the pulsating, that is dynamic component of wind, decrement of vibration for steel structures. Here both are added in the drop down list. For concrete it is 0.3 and for steel it is 0.15. For this decrement value we need to refer table 8. For that page number, so for the decrement of vibrations we need to go for page number 19. So here in this highlighted text, highlighted lines in the right hand side of a PDF, you can see that for A, reinforcement concrete is 0.3, and for steel towers, mast line, chimneys, columns means it is 0.15. So likewise, we need to select based upon our structural materials and the limiting frequency of a structure, that is as per table 8. For that page number 18 to be referred. So here is a table for that. So that decrement of vibrations, we know that 0.15. So here as per the wind region, which for us it is 2, we had selected in the top most line. So for that 2 and the decrement value 0.15, the limiting frequency of a structure is 3.4. So this is also directly picked up from the table of code reference which is shown here. Yes, this is a table for limiting frequency. So next one is in wind parallel direction. We are assuming that structure is 2 meter wide and height we already assigned as 10 meter.
So for that we need to find out the pulsating component of wind. So for this formula we need to refer page number 17. So here you can see the formula which is in highlighted text in the right hand side PDF. WP equal to Wm into zeta rho. So here the definition for zeta and rho are given here in the below lines. So for coefficient of wind pressure pulsating at the height z that is adapted, we need to refer table 7. So this is a table 7. So for locality category A and height of the structure 10 meter, the value is 0.76. So that this is considering here. So this value had arrived by using this table format here. The zeta value is applied by various, because that height is given in the standard is 10 meter, 20 meter, and between the 20 to 40 meter there are some 10-meter gap, and also there are some certain gaps are there, so that this table is converted to here based upon the interpolation process, and thus we are finding this zeta values 0.76. And the next one is a spatial correlation factor. For this we need to refer table 9. For that page number 18 to be referred. So here you can see the table 9. Sorry, it is page 19. So here this is a table to find out the spatial correlation factor. So for width direction 2 meter and for height direction 10 meter, the value is 0.89. So this is again calculated in this table code reference, which is shown here in the left hand side of Excel sheet. So likewise, both the value is required for calculating the pulsating component of wind, that is wind pressure pulsating coefficient is 0.76, and spatial correlation factor is 0.89. So both the things we had calculated using the table showing here in the left side of right side of left hand side Excel sheets. Now we are in the final stage of calculating the wind pressure. Now the total wind pressure equal to WEZ equal to WMZ plus WPZ. So by adding these two value, we will be getting this 1.01 kilonewton per square meter. So this is a total wind pressure. Now this wind pressure to be applied on the various structure as per our requirement. So with this, let me end this. Thank you. Look description for more related videos.